Hey guys, and welcome to another Core Pure revision video. Today we're taking a look at Argand diagrams, and I am omitting like locus and regions of Argand diagrams only because I think it deserves a separate video. So in this video, I'm mainly looking at the modulus and argument of a complex number and modulus argument form. Okay, and obviously just sketching Argand diagrams and representing complex numbers on an Argand diagram. So the first question, hopefully a nice easy one that I've picked out here, exercise 2b, question 3. So question 3, just get the right pen colour. So we're asked to show Z on an Argand diagram. So question 3 here. So what's Z? Well, Z is minus 40 minus 9i. Okay, so just one mark for this because hopefully it's nice and straightforward. So if I draw my sketch, so just remember which axis represents the imaginary and which one represents the real numbers. So the real numbers is what would be our x-axis, and then the y-axis represents the imaginary numbers here. Okay, so minus 40 minus 9i, so that's minus 40 along the real axis, and then minus 9i on the imaginary axis. So we're going to go 40 to the left on the real axis. So my sketch isn't very good, but you get the idea. So let's just say that's there, and then we've got to go down 9. So let's just say that's there. It doesn't have to be perfect, it's just a sketch. So if I call that Z there, so Z is minus 40 minus 9i. Okay, and then part B just asks us to calculate the argument of Z. So arg Z, that's the argument of Z. So how would we do that? Well, consider kind of sketching this triangle so you can see what's going on. So we're going 40 across, so from here to the origin that's 40, and then from here to this point here that's 9. So let's just sketch this. That's 9. So we have this triangle here, and the argument we want to find is this angle here. Okay, that's what we want to find. So if we call that alpha, that's what we want to find there. So how do we do that? Well, we just use trigonometry. Okay, so this would be opposite here, so this would then be the argument. Obviously this is the hypotenuse, so we use tan inverse of opposite, which is 9 over, and then over the adjacent, which is 40, so 9 over 40. But we have to be careful because this doesn't just give us the argument, so you've got to consider what quadrant you're in as well. So let's just work out this first. So tan inverse of 9 over 40, working in radians here, because we need to get the answer in radians, so obviously make sure you calculate this in radians. This gives 0.2213, so on and so on. So therefore alpha is equal to this. So when you're in the third quadrant, remember the argument is defined as minus pi minus alpha here. Okay, so what I need to do is work out pi minus alpha and then work just times it by minus 1 essentially. So minus pi minus 0.2213, and what would that give me if I went out to 2 decimal places? You should get minus 2.92. Okay, so that's the argument there for this complex number Z. So hopefully a nice easy one to get started, but it's just going over the key concepts of an Argand diagram there and being able to work out the argument of a complex number. So the next question is, we're given the modulus and we're actually given the argument as well. We're asked to then find the complex number using this information. So how would we do a question like this? Well, to do a question like this, we need to use the Mod-Arg form. So Z in Mod-Arg form. So this is modulus argument form. How would we do that? Well, the first thing we know is that the modulus of Z is equal to 5. So if the modulus of Z is equal to 5, remember for Mod-Arg form, we represent a complex number as being equal to Z equals the 5 here, which when you square that and then take the square root, you get this argument, this modulus here. So that has to be 5 again. You square that and then take the square root, you're going to end up with 5. So that's the R there, so I should write it as R times cos of the argument, so let's just call that arg Z And then we had plus I sine argument of z again. So argument of z, but I'm running out of room. Okay, so that's just the idea there. So we've got the argument, that bit's easy. We've got that there. And then the r is just a bit at the front. So our complex number, we can just write this as z equals 5, because that's what it is for our question here. Cos the argument is minus 4 pi over 3, so we just literally put that in, minus 4 pi over 3. Plus I sine 4 pi over 3 again, or minus 4 pi over 3. Okay, but obviously we need it in the form a plus bi, so we're going to have to do a bit of manipulation here to get into the correct form. But what I can do is I can expand this separately, so 5 times cos minus 4 pi over 3, and then 5 times I sine minus 4 pi over 3. So doing that, we get 5 cos minus 4 pi over 3 plus 5 I sine minus 4 pi over 3. Okay. Again, we're still not in the correct form. We're going to have to do a bit more manipulation. So how do I get to the next step here? Well, to get to the next step here, we just have to consider these functions, these trig functions. So cos of minus 4 pi over 3 and sine of minus 4 pi over 3. So using the fact that cos of minus 4 pi over 3, if you need to work this out, just put it in on your calculator. Cos of minus 4 pi over 3, that's minus a half. And then sine, so sine of minus 4 pi over 3. What would that give us? That gives us root 3 over 2. Okay, so we're just using this fact now. Obviously, we're timesing this by 5. So my first part here is 5 times minus a half. So therefore, this equals 5 or minus 5 over 2 plus 5i times root 3 over 2. So plus 5i root 3 over 2. Okay, so we have it in the correct form now. We've got a and we have our b here. So therefore, a is equal to minus 5 over 2 and b is equal to 5i root 3 over 2. Okay, so again, not a particularly challenging question, just making sure you're aware of the key concepts between going from the modulus and the argument here at the beginning of the question to Mod-Arg form, and then just simplifying to get the complex number. Okay, so hopefully that's okay. Where a and b now are our exact real numbers. So next question here is looking at basically the roots of an equation. And this equation is a complex equation here, because we've got z squared plus 5z plus 10. You go to factorise that, it's not going to end nicely, because the discriminant of this is negative. Okay, so there's two ways you can do it. You can complete the square, or you could use a quadratic equation, a quadratic form if you want. So it's completely up to you. I'm going to complete the square here because I think it's a quicker way of doing it. And obviously I like saving time, so let's jump into that one. So completing the square here for question 1. So completing the square. So half this b term here, so 5 over 2. So that's z plus 5 over 2. We square this expression here. We take the negative square, so if you square 5 over 2, that's 25 over 4, but we take it negative, it's minus 25 over 4. And then we add on what's left, which is the 10, so plus 10. And we know all of that is, like we're told in the question, f of z is equal to 0. So don't forget, this isn't any different to f of z in the question, it's just a better way of rewriting it to solve it. So now I can simplify this bit here. That's z plus 5 over 2 squared. If you do minus 25 over 4 plus 10, that'll give you plus 15 over 4. And that's equal to 0. So therefore, z plus 5 over 2 squared is equal to minus 15 over 4. Okay, so now we just need to solve this. So if I take the square root of both sides here, we can then just go about solving it. So take the square root of the left hand side, that just gives me z plus 5 over 2. That's going to be equal now to the plus or minus the square root here. So this is equal to the plus or minus. So make sure you take both square roots here, plus or minus. The numerator, well, don't forget this is negative for a start, so we're going to need the imaginary unit. The numerator, well, that would be root 15, because we can't simplify that any further. The denominator would be root 4, which is equal to 2. So what we get here is root 15 over 2i. Okay. So now we just need to keep simplifying this here. So therefore, I'll just keep solving. Z is equal to basically this minus this. Minus this off both sides, we just get Z on its own. So minus 5 over 2 plus or minus root 15 over 2i. Okay. So that's just Z there. And obviously we get two different solutions. We're going to get minus 5 over 2 plus root 15 over 2i, and minus 5 over 2 minus root 15 over 2i. So then the next part just asks us to show this. So again, if I do a bad sketch, just to illustrate it. So don't forget, this is your real axis, this is your imaginary. So if I say Z1 is equal to the positive 1, so that's minus 5 over 2 plus root 15 over 2i, and then Z2 is the conjugate of this, so minus 5 over 2 minus root 15 over 2i. So then we can represent both of these on my Argand diagram. So if we start with Z1, it's minus 5 over 2 on the real axis, so that's about minus, well, it is minus 2.5, so we'll say about there, and then it's up root 15 over 2. So again, it just needs to be a bit of a rough sketch. If we say that's about there, so that's Z1. And then we can do the same with Z2. Again, it's minus 5 over 2, so it's going to be exactly there. And then it's down root 15 over 2. So if we say that's about there, and that's perfect. Like we said, it's a complex conjugate, so it should be this reflection. If this looked crazy and it was somewhere over here, we'd done something wrong. Or if it was over here, again, we've quite clearly done something wrong. So it should just be a reflection here in the x-axis. So hopefully that's okay. Just one mark for showing them roots on an Argand diagram. So it shouldn't be anything too crazy. But yeah, there we go. So the next question, another one from the mixed exercise 2 here. We've got our complex number z defined by this quotient. So part A asks us to find the modulus of z, and part B you're asked to find the argument of z. So let's have a go at this. So we've got z here, 3 plus 5i divided by 2 minus I, and we want to find the modulus of this. So you've got to find the modulus of this, but at this stage this is a little bit tricky to work with. We can make life much easier. And how would we do that? Well, we just times it through by the complex conjugate. So remember the complex conjugate. So this is 2 minus I in the denominator. We're going to times both top and bottom by 2 plus I. 2 plus I, numerator, 2 plus I in the denominator. Okay, so doing that, what would I get here? So I've got 3 times 2, so that's going to give me 6. We're going to have 3i here plus 10i, so I'm going to get 13i. And then I've got 5i squared, 5i times I get 5i squared. So that's my numerator. My denominator is even easier. All you need to do is consider this as the difference of 2 squares. So I can just times 2 and 2 together, and then minus I, and then I. The other terms will cancel. So 2 times 2 is 4, and then minus I squared. Okay. So we can simplify here. Remembering the fact that I squared is equal to minus 1. So I squared is equal to minus 1 here. So basically, using that fact, we can simplify because this is 5 lots of minus 1, so minus 5. So that's going to give us 1 plus 39 in the numerator. So 1 plus 39 divided by 4 minus 1. So that's 4 plus 1, giving us 5 in the denominator. So now we need to work out z. or write z in an easier way, just so we can work out the modulus. So that's going to be a fifth plus 13 over 5 I. Okay, so now we've got it in this form here. Now we can work out the modulus in a much easier style. So remember, that's the square root of both of these elements here squared. So that's going to be a fifth squared plus 13 over 5 squared. If you work this out, what you'll get is you'll get 170, or the square root of 170 divided by 25. So using your rules here for surds, we could write that as square root of 170 over the square root of 25. And obviously this will just simplify here to be root 170 divided by 5, or a fifth of square root of 170. So there we have it. So that's the 4 marks there for the argument, the modulus of z for part A. And then part B, we just want to find the argument of z. So argument of z. So how would we do that? Again, I would recommend it for all the argument questions that you've got to do. Just draw a little sketch just to illustrate the problem at hand. So, it doesn't have to be perfect. My art skills are terrible. So what is our complex number? Well, our complex number here is z. So it's a fifth plus root 13 over 5 I. So a fifth, let's just say that's there. 13 over 5, let's just say that's there. So that's z. So what have we got here? Well, we're going a fifth across here on the real axis, and we're going up 13 over 5 on the imaginary. That's 13 over 5. Okay, so what's it called? The angle we're looking to find here, alpha, is this angle here. Okay, so don't forget, this is opposite over adjacent again, so we need to use tan. So this is tan inverse now of the opposite, which is 13 over 5, divided by the adjacent, which is 1 over 5. So what this is now is 13 over 5 divided by 1 over 5. Okay, working this out now, we get tan inverse of, well, essentially if you actually calculate this is tan inverse of 13, which if you work it out, that's 1.49 radians. Now at this point here, you can work this out in degrees if you prefer. There is no specification in the question as to whether it's degrees or radians, so either's fine. I'm looking at it in radians, just going to calculate it already in radians, but either is absolutely fine. So it's 1.49 radians, and do we need to do anything else with our quadrant? Well, we're in quadrant 1 here, and remember, when you're in quadrant 1, it is literally just that answer there. So once you've calculated tan inverse here, that's just that answer. So therefore, alpha, the argument of z, is equal to 1.49 radians. Okay, so there we have it. So that's that question done there. And we're moving on to the very final question here. Again, just a small one. But, you know, again, practicing the rules, being confident with the modulus and the argument of a complex number. Question 14 here, I can't speak today, from review exercise 1. We've got two complex numbers, we've got Z1 and we've got Z2. So part A is a show that question. So basically we know whether we're right at the end or whether we've somehow got it wrong if we can't get there. And then part B is a find the argument. So for part A, what I'd do here is I'd just work out both moduluses individually. So modulus of Z1, well, that's going to be the square root of 5 squared plus, so just because it's I, don't think of that as anything else other than just 1. It's 1I. Okay, so that's plus 1 squared. So that's root 25, so it's the square root of 25 plus 1, so root 26. The modulus of Z2 here, well, what would that be? Well, that's going to be a square root of minus 2 squared plus 3 squared here. So what would that give us? So that's 4 plus 9, so that's root 13. So what we're actually asked to find or show is that the modulus of Z1 squared is equal to 2 lots of the modulus of Z2 squared. So if you think about this, using this fact that modulus of z1 is equal to root 26, if you square this modulus here, you're just squaring the final solution. So if you square root 26, you just get 26. Same again with z2. The square of z2, or the modulus of z2, will just give you 13. So therefore, that's 26. And z2, the modulus of z2 squared, that's 13. So therefore, this 26 is equal to 2 lots of 13. So therefore, modulus of z1 squared is equal to 2 lots of the modulus of z2 squared there. Okay, so hopefully that's nothing too tricky. Again, for a question like that, break it down, work out both sides individually, and then just see if you can piece it together, almost like a bit of a jigsaw. Part B, you have to find the argument of z1, z2. Now, there's two ways that you could do this. You could work out z1 times z2, and then take the argument. I think that's a nicer way of doing it. You know, you can do it all in one step. You could also work out the argument of z1, and then work out the argument of z2 individually, and then add them together. That's the other way we could do this. I'm going to take the method of the first one, so working out the product of z1, z2, and then taking the final argument. So z1, z2, so that's z1 times z2, so that's 5 plus I times minus 2 plus 3i. So 5 times minus 2, that's minus 10. We've got 8i there, minus 2i. Oh, sorry, that's 15i minus 2i. So that's 13i. I can't do basic maths. And we just get plus 3i squared. Okay, so nothing too tricky there. Simplifying this, so this is minus 10. Remember, I squared is minus 1, so 3 lots of minus 1 is minus 3. So that gives us minus 13 plus 13i. Okay, so we want to find the argument. So like we always do, we go back to drawing our sketch here. So what are we looking to find? Well, we're looking to find the argument of this here. So this is z1, z2. So that's minus 13 on the real axis. So let's just say that's there, and up 13. So let's just say it's there. So that's z1, z2. So now, if you think about this, that's 13 across, and it's also 13 up. Okay, 13 along the imaginary, 13 along the real. So again, the angle we're looking for is this one here. We call it alpha. We're looking for this angle here. So to do this, again, just like we have done for the previous ones, we're going to do tan inverse because it's the opposite over the adjacent. So this is tan inverse of 13 over 13. So that's the tan inverse of 1, which is hopefully something that you just kind of memorise. That's pi over 4. But again, you could work in degrees here if you prefer. It isn't specified in the question, so either is acceptable. I'm working in radians still, so that's pi over 4. But you're in the second quadrant here. So remember, if you're in the second quadrant, the rule is pi minus alpha. So pi minus alpha. So in our case, that's pi minus pi over 4. Okay, so that'd be 4 pi over 4 minus pi over 4. So we get 3 pi over 4 there to finish with. Okay, so hopefully this has been not too tricky of a lesson. It's one of the nicer kind of topics within this core pure book. You know, definitely just walking through basically the introduction to complex numbers. But I will cover regions and locus of complex numbers and the Argand diagram in a separate video. So that will definitely be coming. But I hope this helped. Any issues, any mistakes I've made, please just let me know down below.